what I wanted to do today here so that we can at least kind of set the stage for what we're going to talk about next before tomorrow, and when we go through a whole bunch of new reactions here, is to see again some of the commonalities that we've been talking about so far this summer and how we're going to apply this to other new reactions. And this area here of these carboxylic acid derivatives, as I mentioned at the beginning of today, this is one of the big deals in our class for this second semester of organic chemistry. It's going to look like, again, a lot of very similar reactions with some subtle differences. In fact, if it does look like that, it's because that's the way it is. But hopefully, if we look at this systematically again, from a mechanism point of view, things will make sense. So let's go all the way back now to, I guess it was 2 weeks ago. Some ways seems short, some ways seems like a long time ago, on the first day of our class. And we went through comparing two general mechanisms of reactions. And so I sketched them out here so we don't have to rewrite them. What we've been dealing with here now for the past 2 weeks are reactions, say, of aldehydes and ketones. So we either have a hydrogen there or not. And we have a nucleophile that can attack. We generate this sort of an intermediate. This might be hydroxide or a Grignard reaction or something of that sort. But in this particular case, in the simplest sense, now we have no good leaving group. There are always exceptions, but we're going to say there's no good leaving group. So what we can do, because we have a carbon or a hydrogen, add in a little bit of acid or water, protonate to generate our product. So we've added our nucleophile to the carbonyl group. What will be different now, so scroll up a bit here, is with these carboxylic acid derivatives. And so these are all based on the carboxylic acid, where you have OH here in the place of OR. And even though they're called carboxylic acid derivatives, the carboxylic acid itself is not the most important one here. But now with the ester here as an example, so an ester is a C double bond O, OR, R is some alkyl group here. Now in the presence of a nucleophile, same thing as before, the nucleophile will attack, move these electrons up into this oxygen. We have this tetrahedral intermediate in the middle, just like before. But now what we have is a leaving group. Here, let's make that green match my pen. So we have a potential leaving group. So now what we can end up doing is reforming the carbonyl group and kick out the leaving group. So now what we've ended up doing is we've substituted, say, OR versus whatever our nucleophile is. And then this is our leaving group. So in this particular case now, we're carrying out a substitution reaction. We have a nucleophile. It's occurring at a carbonyl group or an acyl group. And we're carrying out a substitution, as opposed to having a nucleophile and an acyl group, and we're adding something. So what the key thing to notice is the first step of the reaction is the same. The nucleophile attacks the electrophilic carbon of the carboxylic acid derivative, generate this tetrahedral intermediate, and then kick out our leaving group here to reform the carbonyl group. I should point to this. And our leaving group is left. Now, what we'll see is that a lot of times you might have two leaving groups. So you have this OR as a leaving group, and maybe the nucleophile, or what was the nucleophile, could also be the leaving group. And indeed, at times, that will also leave. And then you just get back to the beginning step of the reaction. So if you come down here, kick out the nucleophile, you're going to still be stuck with OR at that position. So those things will happen behind the scenes. But eventually what we'll end up seeing is that a lot of times this group will be the better leaving group, and that's what's going to drive the reaction forward. So we're going to see a variety of carboxylic acid derivatives. We're not going to emphasize the naming of these species. Probably saw that back in the beginning of OChem 1 where he talked about nomenclature. But we're going to have to get comfortable now with a variety of different carboxylic acid derivatives, as is indicated here. And I put these in an order that sometimes is known as the ladder of reactivity. And this is useful to know because it allows us to predict a lot of the reactions we're going to see. What we'll end up seeing is that this acyl chloride species We have a chloride here. This is the most reactive carboxylic acid derivative. And down at the bottom, this amide that we have here is going to be essentially the least reactive. And this nitrile, our C triple bond N, at the very bottom, this is tossed in all of these different carboxylic acid derivatives because it has a similar behavior and reactivity, but it doesn't really fit this ladder of reactivity. So we're going to draw a line there to show that that's not part of it. But what we can see is as we go from the least active, we have the amide, carboxylic acid, ester, thioester, and hydride to the acyl chloride. That's our most reactive species. So we're increasing reactivity as we go up the ladder. Now it is possible to have something like an acyl bromide, but those end up being far too reactive to actually deal with. And then I had fluorine on here in our exam as a question about the hydration reaction to get back at the fundamentals of electronegativity. You don't really see acyl fluorides here just because fluorine in this context of reacting with other nucleophiles will behave a little bit differently. Still follows the inductive effects that we saw. So the reason for organizing these structures in this way is if we have something that's high in reactivity like an acyl chloride, we'll see it's quite easy to turn this into an ester or a carboxylic acid or an amide or for example, or even an hydride. So in terms of the chemistry, we can go down the ladder. If you have an acyl chloride, you can pretty much make any one of these derivatives from it. We can just use a variety of different nucleophiles to attack. However, if you have an amide or a carboxylic acid, for example, it's much harder to go up the ladder because you're making something that is less stable. So the carboxylic acid is more stable than the acyl chloride. And we'll see there is a reaction. There are a couple of reactions to go up the ladder. So those are going to be very important for our general perspectives here. But most of the time we'll think about going from something that's much more reactive, like the acyl chloride, to make it something that's much more stable, like the carboxylic acid. And then just to reiterate again, the nitrile here we'll include in our list of derivatives, but it doesn't quite fit in the order of the reactivity. So now what I'd like to do here, and so I left this space here on the side, is I want to think about what is the difference in reactivity of these species. So why is the acyl chloride so much more reactive than the amide? So let's look at the two structures on the end here, the ladder. Let's just put it over here and see if we have room. So why is there a difference? And for space will be grammatically incorrect. You can think about two things: resonance and leaving group ability. There are others, but we'll consider these right now. So let's compare these two by looking at the structures. So let's draw our acyl chloride here, and let's put in everything that we have. Let's put in all the lone pairs of electrons to help show this, and draw a resonance structure. We can imagine these electrons in the chlorine. We'll just draw the both at one time. So I have a carbon-chlorine double bond, and put the negative charge on the oxygen. Chlorine's given up electrons, so it has a positive formal charge. So let's consider this, and let's consider the same thing now for the amide. And we'll just put two hydrogens here. So we could also draw a resonance structure. The thing likes to pop up on the bottom. I think I'm touching something in the corner. Okay. Let's move these electrons here up onto this oxygen. So I have a positive formal charge on the nitrogen. Okay, so pretty messy in the way they're drawn, but these are both valid resonance structures of the starting species. And so our acyl chloride and our amide and a resonance structure of each one. Now, a few minutes ago, we had this, again, it was a hand-waving argument that the carbon-phosphorus double bond was not very important for the Wittig reagent, for that ylide, in terms of a resonance structure. And we attributed to this poor orbital overlap. And we can actually say a similar thing here. Let's go with blue. So carbon-oxygen, this bond, let's squeeze it in here. So carbon and chlorine as well, due to their different locations on the periodic table, chlorine being much larger, there's poor orbital overlap. Whereas with nitrogen carbon, there's a very favorable orbital overlap. What this means is that this resonance structure here, in which having the chlorine donating electron density into the carbonyl carbon, is not very favorable. So this chlorine here doesn't really do this very much. So it's not really donating electron density to this carbonyl carbon in this particular case. Whereas the nitrogen can donate a lot of its electron density into that carbonyl carbon, which means that this right resonance structure is a significant resonance structure. So this one, a lot of colors going on here. So this is a minor resonance structure. Whereas with the amide, this one is a major form. So what we're doing, and I'll write it down here in the bottom because I have a lot of things kind of squeezed in here, is it goes back to our exam question as well. Remember, we're thinking about having a nucleophile attack the carbonyl carbon here. And so what we're dealing with here is this is our electrophile. So anything that is withdrawing electron density away from this carbon should make it more reactive, should allow our nucleophile to attack. And we can consider what are the different features of these species that could change the electrophilicity of this carbon. One is we have all of these substituents with lone pairs of electrons, so they could actually dump electron density back in to the carbonyl carbon, which will make it less reactive, more electron density in this oxygen. And here we're saying we can draw resonance structures actually we're just using the acyl chloride and the amide. However, what we're saying is that for the acyl chloride, this doesn't really contribute much, which means the chlorine doesn't really dump electron density back into the carbon due to this poor orbital overlap. So that doesn't really decrease the electrophilicity here. But it does for the amide. So the amide, you can dump electron density back in here, making this carbon less positive. So that should make the amide less reactive than the acyl chloride. So that's one feature. And these other ones are going to be somewhere in the middle there. The chlorine, though, however, is highly electronegative. So why don't we use this magenta color? So it's pulling electron density away from that carbon. So instead of donating through resonance, it's actually pulling electron density away through induction. And the electronegativity difference of carbon and chlorine is going to be bigger than carbon and nitrogen. So that means this is just really making that carbon even more electrophilic, more reactive overall. So that should increase the reactivity of this. And then last is going to be the leaving group ability. So in this particular case, I'm going to save much space here. Let's have a nucleophile attack. I have a negative charge there. Tetrahedral intermediate. Let's draw it as a one-way arrow here. Our generic mechanism. Chloride as a leaving group. Kick out the chloride. will reform this plus generated chloride. And we can put in all these lone pairs of electrons this time. So our leaving group here is going to be Cl minus. And that's a good leaving group. It was a good leaving group for SN2 reactions. That's the conjugate base of HCl, a strong acid. So the chloride can really help stabilize that negative charge. That's why it's a good leaving group. Compare that to, if we can squeeze down one more thing here, our amide, our same nucleophile, generic, is going to attack tetrahedral intermediate. This actually doesn't happen, but we'll use it just to demonstrate. And then kick out NH2. This is a horrible leaving group. So we made this, the nucleophile, plus NH2 minus. Oh no, all the way back up, okay. NH2, and then this had a lone pair, nitrogen had a lone pair in each of these cases. Now it has two lone pairs. So this is a bad leaving group. So this is a great leaving group. It's a bad leaving group. So this is amide, NH2. So it's a very strong base. This compound really, if you want to think about it, wants a proton because it's so unfavorable to be formed as that amide. So that means kicking out this NH2 as NH2 minus is highly energetically unfavorable. However, kicking out chloride to form Cl minus is quite energetically favorable. So to go back up for a minute here to see where we're at, so there's a lot of things scribbled on here. We're going to see these different carboxylic acid derivatives shown here in this ladder of reactivity. The most reactive here being the acyl chloride are the ones that we're considering. On down in terms of different reactivities, and the amide is down here at the bottom. It's one of the least reactives. And conceptually, we want to start comparing why do we actually see this difference in reactivity. And there's a number of different reasons that can contribute. But it comes back down to thinking about, just like with aldehydes and ketones, we're thinking about what affects the electronegativity of the carbon, of the carbonyl group. We can do the same sort of analysis here. When we see with the acyl chloride, it doesn't really donate electron density back to the carbon, as depicted in this resonance structure. And we said that's due to this orbital overlap that's not very good. And instead, the chlorine is pulling electron density away due to an electronegativity argument. So that makes this species quite electrophilic. And on top of that, we have a really good leaving group, because this leaves as Cl minus. On the flip side, this nitrogen is not really pulling electron density away due to electronegativity. It was actually donating electron density back through this resonance structure. And so that makes this carbon less reactive compared to the acyl chloride on the top. And then on top of that, the leaving group is really bad. So we end up having an NH2 minus leave, which is unfavorable. So all of those features are going to make this amide much less reactive. So a lot of things to consider for the differences in reactivity. And you'll notice these are also features of a peptide bond. For those interested in biochemistry, which also makes it much more difficult to break a peptide bond. But that's what happens in digestion. And so that's why we have enzymes that can cleave the peptide bond. And I just took out these two examples, going to the left here, acyl chloride and amide. We might start thinking about how, maybe the oxygen is not quite as unfavorable to leave as compared to the amide, and the carboxylic acid and the ester is somewhat similar. Sulfur is going to be a better leaving group. It's going to donate electron density less effectively, so the thioester will probably be more reactive than the ester. And then this one here we're going to see has a really good leaving group on it because we have resonance stabilization. So in general, to Kyle's questions, as long as they're in the same period, a lot of times you'll see much better orbital overlap. But as you start going down the periodic table, even in the same group, then the valence electrons are in different shells, and so that you have less favorable orbital. So if you're looking at something like carbon up near the top versus chlorine down quite a ways. The valence electrons in the chlorine are in a much larger orbital, so there's going to be very little overlap with the carbon. But if you have things like carbon, oxygen, and nitrogen, they all overlap quite well. So great question.